In this video, we are going to examine stereochemistry of molecules with multiple chirality centers. Now we are going to examine molecules that contain more than one chirality center. And that will also lead to concept of diastereomers. So we are going to learn what are diastereomers. First, if molecule has more than one chirality center, then of course it has greater number of stereoisomers. Maximum number of stereoisomers can be determined by application of Van 't Hoff rule, where number of stereoisomers equals 2 to the power of m. You may recall that you have already encountered Van 't Hoff rule when we studied polyenes, dienes, trienes, tetraenes. And then Van 't Hoff rule was formulated as 2 to the power of n, where n was number of double bonds. Now, just to be different, I'm using m for number of chirality centers. So if there are two chirality centers, then maximum number of stereoisomers is 4. Of course, there could be fewer than that if symmetry is present, as you will see later, but maximum number is 4. And one example of molecule that indeed has 4 stereoisomers is 2-bromo-3-chlorobutane. So 2 chirality centers and 4 stereoisomers. And here are formulas, Fischer projection formulas of all 4 stereoisomers. You can see that there are 2 pairs of enantiomers, 2 pairs of mirror images. One on the left and 2 compounds on the right are another pair. So that constitutes all 4 stereoisomers. And you can see here one pair of enantiomers shown in green box. And to the left, the same pair is represented as perspective drawing, and that's perspective drawing of the Fischer projection. And you can see that this is a representation of molecule in least stable eclipsing conformation, but that's also the most symmetrical conformation. So while this is the least stable conformation, this is not conformational analysis. We are interested in stereochemical analysis of molecule, not conformational analysis. So we can use least stable. In fact, we need to use the least stable conformation because the least stable conformation is usually the most symmetrical conformation. And that's one that we need in stereochemical analysis. That's why Fischer projections are so useful, because they represent molecules in the most symmetrical conformation. And you can see from this example, and that's generally true, that if 2 molecules are mirror images of each other in Fischer projection, then they are enantiomers of each other. And that's consequence of the representation, that it's the most symmetrical representation. Here we have a pair of diastereomers. Diastereomers are stereoisomers that are not mirror images of each other. So any 2 stereoisomers of particular molecule, particular compound, that are not mirror images of each other are related to each other as diastereomers. And this is summarized in this table here. So again, we have 4 stereoisomers of 2-bromo-3-chlorobutane, and you can see in red relationship is shown as enantiomers. So they are pair of enantiomers. So on the top we have pair of enantiomers, and on the bottom pair of enantiomers. Any other 2 pairs are related to each other as diastereomers. If you wish, you can pause video here and analyze this table a little bit more. So pair of enantiomers, another pair of enantiomers, and any other pair of compounds are diastereomers of each other. When molecule has 2 neighboring chirality centers, there is possibility for Erythro threo isomerism. That's the case when we have what we call 2 contiguous chirality centers. That's contiguous, not contagious. We already encountered that in this course. So 2 contiguous chirality centers, meaning 2 chirality centers that are next to each other. And you can see here Fischer projections of 2 such examples. Then there is possibility for Erythro threo isomerism, and isomerism is named after 2 carbohydrates, 2 tetrose carbohydrates called erythros and threos. So if in Fischer projection 2 similar or identical substituents are on the same side, then that's Erythro isomer, named of course after erythros. And if 2 identical or similar substituents are on the opposite sides, that's threos. That's threo isomer named after threos. And so when we go back to our previous example of 2-bromo-3-chloro-butane, then we can see that there is trio pair of enantiomers, where bromine and chlorine are on the opposite sides of Fischer projection, and of course 2 hydrogens are also on the opposite sides. And there is Erythro pair of enantiomers, where 2 halogens are on the same side of Fischer projection and 2 hydrogens are on the same side. So in case of contiguous chirality centers, typically we can identify erythro and trio pair of enantiomers, while erythro and trio molecule are related to each other as diastereomers. Note that it's best to use Fischer projection to recognize erythro and trio pair of enantiomers. Here, erythro and trio pair are shown in various perspective drawings, and you can see that it's considerably more difficult to identify which one is erythro, which one is trio. It's not impossible, and you can learn very quickly. If you wish, you can pause video here, and you can learn very quickly how to identify it from perspective drawings, but obviously it is much easier to do that from Fischer projections. Note that for stereoisomers of molecules with 2 chirality centers to be designated as erythro and trio, chirality centers have to be contiguous. They have to be next to each other. If a molecule has 2 chirality centers, but they are not contiguous, then we may still have 2 pairs of enantiomers, a total of 4 stereoisomers, but they cannot be designated as erythro and trio. And here is one such example. So this would be 2-bromo-4-chloropentane. So still we have 4 stereoisomers, pair of enantiomers on the left, pair of enantiomers on the right, and in Fischer projection in one pair both halogens on the same side, both halogens on the same side, in the other pair halogens are on the opposite side, 2 hydrogens on the opposite side, but nonetheless we cannot say that one of these pairs is erythro, the other one is trio. We simply don't have names for these pairs of enantiomers. It's simply 2 pairs of enantiomers, and we'll designate them, as you will see at the end of this video, by using simple designation R and S. Now, cyclic compounds obviously exhibit chirality, and we need to consider symmetry in cyclic compounds, because obviously cyclic compounds, by having cyclic chain, basically chain folds on each other, are more symmetrical. To consider stereochemistry of cyclic compounds, we use these a little bit odd perspective drawings that are called Hayward projections, where ring is represented as flat. That's obviously the least stable conformation, but as you know, we already mentioned that least stable conformation is most convenient. It's the most symmetrical for stereochemical analysis. So this is how we represent rings, as being completely flat, and then substituents pointing straight up or down. Again, very unstable conformation. So that allows us to clearly identify symmetry elements. And so you can see that in these cases, compounds, these 4-membered rings and 6-membered rings, don't have any chirality centers. Even though each ring has 2 carbons with 2 different substituents, remaining 2 substituents are identical, because line that bisects the ring, that divides the ring into 2 equal halves, bisects rings actually, as I said, into 2 equal halves, 2 identical substituents. So these compounds are not chiral. But these compounds are chiral, and each of them has 2 chirality centers. So on the top we have 5-membered ring, on the bottom 6-membered ring, and you can see that if you do the same exercise, you can pause the video here and do the same exercise on each chirality center, bisect the ring into 2 equal halves, you will see that each molecule has 2 chirality centers, and that means 4 stereoisomers. The top one, actually we can talk about erythro and trio, but in cyclic compounds we usually talk about cis and trans. So for the top one, we could maybe stretch nomenclature a little bit and say that left pair of enantiomers, 5-membered ring, is erythro, right pair trio. But really we call them cis and trans. So for the top example, for 5-membered ring, that would be 1-bromo-2-chloro-cyclopentane. We have cis pair of enantiomers and trans pair of enantiomers. And the same goes for the bottom example, 1-bromo-3-chlorocyclohexane. we have cis pair of enantiomers on the left and trans pair of enantiomers on the right. As I already mentioned, Van 't Hoff rule gives us the maximum possible number of stereoisomers that molecule can exhibit. But there could be fewer than that if there is symmetry in the molecule. And that would be the case if we have what is so-called mesoisomer. So the best example is tartaric acid. But we'll look at tartaric acid a little bit later. First, we're going to look at slightly simpler example, and that's 2,3-butane-diol. So in case of 2,3-butane-diol, we have a pair of enantiomers, and that's threo pair of enantiomers. It's shown on the left. But when we look at erythro compound actually has a plane of symmetry. That's another utility of Fisher projections. If we can draw a plane of symmetry through formula that is apparently two-dimensional, actually that's plane of symmetry that is present in the molecule. And if molecule has plane of symmetry, as you have learned at the beginning of this chapter, then it cannot be chiral. So this compound, 2,3-butane-diol, has two chirality centers in its erythroisomer, but it is not chiral. So compounds that have individual chirality centers, but molecule is not chiral, are called meso compounds or mesoisomers or mesoforms. So from this you can see that chirality is property of the entire molecule, not individual atoms. So entire molecule has chirality as its property, so it either is chiral or not. And even if individual chirality centers are present, molecule may not be chiral if it possesses one of the elements of symmetry I mentioned earlier in this chapter. In general, you should be looking only for plane of symmetry. So if symmetry is present, then number of isomers will be fewer than predicted by Van 't Hoff rule. Another way to put it is if each chirality center has the same set of 4 substituents, then symmetry is present and mesoisomer or meso form will be present. Note, in case of erythroisomer, it's 2 formulas that are shown, that rotation by 180 degrees can convert one formula into the other. And that's allowed transformation of Fisher projection, which means that they are the same molecules. And here we have another example, 2,3-dibromobutane. Again, we have threo pair of enantiomers, and erythro is mesoisomer. Note, all of them have the same set of substituents on chirality center. So each chirality center has bromine, methyl group, hydrogen, and this large group that has carbon, hydrogen, bromine, and methyl group. So all of them have same set of 4 substituents. So that's what makes them symmetrical, and of course you can find also a plane of symmetry. So in this case, obviously, there are 3 stereoisomers, pair of enantiomers and meso compound. So 3 stereoisomers. And here is the best known example where this phenomenon was first discovered. That's tartaric acid. So tartaric acid has 2 carboxyl groups and 2 hydroxyl groups on chirality centers. So we can identify threo pair of enantiomers, and erythro is mesoisomer. Note that that's why we have to use Hayward projections of cyclic compounds to identify mesoisomer. So consider example of 1,2-dibromocyclohexane. If you were to look at actual conformations, chair, there are no elements of symmetry. Even both strictly both conformation does, twist both does not, but both conformation would have plane of symmetry. But to avoid any such confusion and looking at individual conformations, we simply use Hayward projection shown on the right. And Hayward projection clearly shows that cis compound, cis isomer of 1,2-dibromocyclohexane is mesoisomer. And so 1,2-dibromocyclohexane would have trans pair of enantiomers and cis mesoisomers, so only 3 stereoisomers. And that is clearly shown here. So trans 1,2-dibromocyclohexane is a pair of enantiomers, while we have seen before cis was a mesoisomer. Now, distinguish mesoisomer from 1,4-dibromocyclohexane. In case of 1,4-dibromocyclohexane, there are only 2 stereoisomers, and those 2 stereoisomers are cis and trans, because 1,4-dibromocyclohexane does not have chirality centers. So we have only 2 stereoisomers, there are no chirality centers. Meso compound is completely different. Meso compound has individual chirality centers, but molecule as a whole is not chiral because it has a plane of symmetry. And here are some other similar examples. So we have example of 1,2-cyclobutane-diol. Trans isomer is a pair of enantiomers. So there's a trans pair of enantiomers, and cis is meso compound. So there are a total of 3 stereoisomers. But on the other hand, 1,3-cyclobutane-diol has only 2 stereoisomers, cis and trans, because it does not have any chirality centers. Nomenclature of isomers with more than one chirality center is indicated by assigning letter R or S, designation RS, to each chirality center, and then we place that in parentheses before the name of the compound, and we also associate numbers with each designation RS so that it's clear to which atom that designation refers to. So here is an example of 3-chloro-2-butanol. If we consider carbon 2, that's carbon with OH group, that one is actually easy to determine configuration. So that carbon is attached to hydroxyl group, that's priority 1. Hydrogen priority 4 is at the back, so we can already ignore it. Now we have 2 carbons on that chirality center. One carbon is attached to chlorine, the other one is methyl group, CH3, attached to hydrogen. So carbon attached to chlorine will have higher priority and methyl group the lowest. So none of that is shown here. I presume that's relatively easy, trivial, and didn't want to clutter the drawing with that. So order of priority is oxygen 1, then carbon to the left 2, and carbon on top 3. That makes a counterclockwise array, and that's S. So that means carbon 2 has configuration S. Carbon 3, one that is attached to chlorine atom, is a little bit more difficult to determine. So that's shown at the bottom. So those arrows shown at the bottom. First, we can rotate molecule about carbon-carbon bond, because if you look at the bottom, you will see that chlorine has priority 1, hydrogen priority 4, and methyl group at the bottom has priority 3. Carbon to the left, one attached to OH group, has priority 2. It should be easy for you to determine those priorities. But you can see that hydrogen points towards you, towards the viewer. So it has to point back. It has to be where chlorine is. So the easiest way to do it is to rotate the molecule so that hydrogen goes to the back, chlorine down, and methyl group up. And that's shown on the right. And now we can ignore hydrogen. And now you can see that 1, 2, 3 makes clockwise array. So designation is 3R, or stereochemistry on carbon 3 is R. So this molecule is 2S3R, 3-chloro-2-butanol. Here is same molecule in Fischer projection. And so here is how you would manipulate Fischer projection. You would move 3 substituents clockwise or counterclockwise while keeping 4th in place to end up with hydrogens on vertical bond, and then you can assign priorities and determine configuration of each chirality center. One other important point has to do with mesoform. If you determine configuration of mesoform, you will find that it's always RS, which means that if you can determine that molecule is mesoisomer, then you don't need to go through whole process of determining priorities and figuring out which one is R, which one is S. Simply it's RS. And of course, let's say for tartaric acid, numbering from top down or bottom up, it's the same 2R, 3S, or 2S, 3R, doesn't matter how you want to number it, it's the same molecule. That's because it's symmetrical. So RS isomer is always mesoform, while pair of enantiomers will be RRSS. So you can determine if something is meso that it is RS without determining configuration. Simply because it's meso, you know it's RS isomer, while pair of enantiomers has to be RRSS pair. That applies only when mesoform is present. If not, then you have to go through the process of determining priorities and determining which one is R, which one is S. This completes our study of molecules with multiple chirality centers, and next we are going to look at reactions of alkyl halides.